Assalamualaikum warahmatullahi wabarakatuh. So today I will explain about chapter 2, which is argument. For argument, we have learned three methods to prove the statement is the statement logically equivalent or not. So what is the method in argument? So we have three methods. First, truth table. Second, rule of inference. And lastly is law of logic. Now we go to the truth table. Okay, first thing first, what we need to know about truth table is how many column we need to put in our table. For the truth table, I will give one example. The question is P is logically equivalent with P or Q. So what we need to do is to prove P is logically implies with P or Q. First thing to know how many column we need to put is how many variable in this statement. So in this statement we have P, Q. So we have 2. So we can calculate 2 is A is equal to 2. So to know the column is 2 the power of A. The meaning that is 2 the power of 2 and equal to 4. Now I will make the table. What we need to do after know the column of the table is we have to put true false true false. So P Q. Okay, so we have to put true false true false true false false. So how can I get the position of true false is you have to put the 2 power of 0 and 2 power of 1 to know put the true false. Okay, so for 2 the power of 0 is equal to 1 and 2 the power of 1 is equal to 2. So that's why for the Q is true false and for P is true false false. So next we look at our example, which is P equivalent implies with P or Q. So after we put P and Q, we look at our statement that what we have is P or Q. P or Q is one of the variable are true, the conclusion is automatically true. For example, is true or false is true, true or true is true, false or true is true, and false or false is false. So we look at the table again. So true or true is true, true or false is true, false or true is true, and false or false is false. Okay, we look at our statement, and the last thing is we need to write this in our table. Okay, I will explain about implies. So for example, P implies Q, we just look of the conclusion. If the conclusion is true, true, false, false, and true, true. But for false, want to be a true, the first will be false. So false implies false is equal to true. Okay, so now we look at our table again. So we look P and P or Q, so that we can prove that P are logically equivalent. P are logically equivalent with P or Q. Okay, so I will explain a bit about the conclusion. If the table in the truth table for conclusion is all true, so the conclusion is tautology. But if the conclusion for the truth table is all false, we call it is contradiction. And lastly, if the conclusion in this table have true false true false true false, and we call it contingency. That's how we prove the statement using truth table.
We're continuing on chapter 3, which is proof. In chapter 3, we have a few methods, which is the forward-backward methods, the construction method, the choose method, specialization, contradiction, contrapositive, and mathematical induction method. Only a few methods we're going to talk about in chapter 3, which is the forward-backward, the construction, specialization, mathematical induction.
Assalamualaikum. Today I will be explaining about the forward and backward method. From the conclusion, we go through a backward process by deriving from it and simplifying it. And from the hypothesis, we use a forward process by expanding on it and to get the same as the conclusion. The question: prove that if XYZ is an isosceles right triangle, then the hypotenuse is square root 2 times as long as one of the legs. So first we write back the question in A and B, hypothesis and conclusion. So first we use the backward process from the conclusion, and then we use Z to represent the hypotenuse, and it is equal to square root 2. The side we use X to represent it. Now we use a forward process from the hypothesis. Since it's an isosceles right triangle, two sides are the same, so we use X is equals to Y. Continuing, we use the Pythagoras theorem, Z squared equals to X squared plus Y squared. Continuing, like I said, we substitute from A1 since X and Y are the same. Z squared is equals to X squared plus X squared. Solving it, we get 2X squared. Completing the Pythagoras theorem, we square root both sides. Therefore, Z is equals to square root of 2 of X. Since A4 is logically equivalent with B1, therefore it is proven by using the forward-backward method. Continuing on with the next question, if triangle ABC is equilateral, then the area is square root 3 over 4 times the square of the length of a side. We write down the hypothesis and the conclusion, AB, and then from B, we go backwards. The area ABC is represented by 1 over 2 base times base times height. For the base and height, I will represent with variable X and Y. And then square root 3 over 4, the side, I will represent with Z using the forward method from the hypothesis. Since ABC is equilateral, all the sides are the same, I will represent it with A, B, and C. Continuing on, since it's an equilateral triangle, it doesn't have a height, so we have to find it using the Pythagoras theorem. Since the height is represented by Y squared is equal to C squared, I'll use one of the sides, minus 1 over 2 the base. Solving the equation, we get, continuing with the forward process, since it is equilateral, we substitute A1 into A3. Therefore C, I'll convert it into A. Solving the equation, we get square root 3 over 2A. Continuing on, A4. We substitute A3 into B1, base times height, since we already got the height, and it is equal to square root 3 over 4A squared. We let D, we pick a new variable, equals to square root 3 over 2A. Then we get A5. The reason we substitute is so that it will become similar to B1. So in the end we get 1 over 2A. D equals to square root 3 over 4A squared. And it is logically equivalent to B1. Even though it has different variables, it's the same thing. So that's all from me.
Construction method, used when the conclusion involves an existential quantifier. Steps in construction method: identify object, certain property, or something happens. Construct the object and show that the object has the certain property and satisfies the something happen. For example, if A, B, C, D, E, and F are real numbers such that AD minus BC is not equal to 0, then two equation AX plus BY equal to E and cx plus dy equal to f can be solved for x and y. So we need to identify our object and something happened. Our object is a, b, c, d, e, f is element to real number, and ad minus bc not equal to 0. And our something happened is b, which is ax plus by equal to e, and cx plus dy equal to f. The first step is to construct x and y. So we use the simultaneous equation. We list down our equation. So what we need to do, we have 1 and 2. So we need to use the elimination. So the first one we need to times with c, because we want to eliminate the dx, and 2 with a. So we got the number 3 and number 4, and we can use the elimination method. So we got this, and then we need to factorize the y, so we need to make the y single. So we need to divide this by ad minus bc, so we can get this, we can get the y. To get the x, we need to take the first equation and times with d, and the second equation times with b, because we want to eliminate the y, so that it can be 5 and 6, and we use the elimination method again, we can get the x. After we get x and y, we can make our a1 and a2, and in the a2 we can substitute the x and y to get the something happen, which is ax plus by equal to e. We can expand the bracket, we can eliminate abf, so it becomes ade minus bce over ad minus bc. In this case, we can factorize the e and cancel the ad minus bc, we can get the e. So we get the first something happen, which is ax plus by equals to e. Next, we can find the second something happen, which is cx plus dy equal to f. We can do this in our a4. So we take the cx plus dy and we substitute the x and y, and we need to expand the bracket and cancel out, which is cde, and it becomes minus bcf plus adf over ad minus bc, and again we need to factorize the f, and we can cancel the ad minus bc, so we can get the f, and we can write it in our a5, which is ax plus by equal to e and cx plus dy equal to f, and which disprove that it is the same with our b, which is the something happen is ax plus by equal to e and cx plus dy equal to f. And that's all from me.
Next, I will explain about specialization. So let's do one question. If R is a subset of set S of real number, U is an upper bound for S, then U is an upper bound for R. So how do we solve this? First, we have to do our A, find our A and our B. Then next, our B, B1. What is our B1? B1 is for all elements, so it will be R less than or equals to U. Our A1, we have to choose an element. Say that is R prime in R. So our B2 is R prime less than or equals to U. For our A2, for all element X in R, so X is in S. We have to specialize A2 in order to get A3. Specialize, we will get our A3 is R prime is in S. Next, for our A4, we have to select the element for all element S in S, that is S equals to or less than U. We have to specialize A4 to R prime. same as A2. So we will get our A5 is R prime less than or equals to U. So as we can see here, our A5 we will get back same as our B2. So that is for example number 1. Alright, so let's try solve another question. For set RST, prove by specialization method that if R is a subset to S and S is a subset to T, then R is a subset to T. So first of all, we have to clarify what is our A and B. Next, our B1. What is our B1? For all element R in R and R T. Our A2, sorry, A1. We have to choose an element that is R prime. Next, our B2, R prime, our A2 for all element R, R, S. Our A3 for all element S. So we have to specialize A3 in order to get A4. Specialize it into R prime. We will get our A4 is R prime S. And lastly, our A5. So we will get R prime T. As we can see here, it is the same. Our A5 are proven with B2. So that's all from me.
The next subtopic is mathematical induction. First, when to use mathematical induction? When conclusion that we assume B has the form for every integer and greater than and equal to 1, something happened. Where something happened is a statement that depends on the integer n. For mathematical induction, we have 3 steps using this method. The first one is verify that P1 is true by replace and everywhere in P1 by 1. The second step is assume that Pn is true, and the third step is prove that Pn plus 1 is true. Start by writing Pn plus 1 and then rewrite Pn plus 1 in terms of Pn. Next, we want to doing some example. Prove that by using mathematical induction for every integer and element of integer, positive integer, and summation of I equal to 1, 3, I minus I equal to and 3n plus 1 over 2. First, we write let Pn equal to summation and I plus I equal to 1, 3i minus I, 1 equal to and 3 and plus 1 over 2. Next, we by following the step, for the first step, we check true for P1. For this step, we just substitute 1 into the equation. For example, we assume that D is right hand side and D is left hand side. For left hand side, we substitute I equal to 1 with 1 and we got 3, 1 minus 1 equal to 3 minus 1 equal to 2. This is for left hand side, and then second we compare with right hand side. For right hand side, as we know this is our right hand side, we just substitute 1 and with 1 and we got 1, 3, 1 plus 1 over 2, 3 plus 1, 4 times 1 equal to 4 over 2 is 2. So this show that left hand side equal to right hand side. Therefore, P1 is true. Since we show that left hand side and right hand is equal, we go to step 2, which is we assume that Pn is true. For this step, we just rewrite the statement, the equation which we taking from the question. We just write Pn equal to summation and I minus 1, 3i minus 1 equal to and 3n plus 1 over 2. Step 3 or last step is we must to check true for Pn plus 1. First we check for right hand side. Like step 2 we compare with right hand side and left hand side. For right hand side, as we know this is our right hand side, we just substitute n plus 1 equal to with n. We substitute n with n plus 1 like that. So n plus 1, 3n plus 1 plus 1 over 2, and we got n plus 1, 3n plus 1 plus 3 plus 1 over 2. We simplify that, got n plus 1 3n plus 4 over 2, and we expand and we get 3n squared plus 4n plus 3n plus 7n plus 4 over 2. This is for right hand side. Okay, next we compare with left hand side. We're doing for left hand side. For left hand side, this is have a special case, which is we know that for left hand side, we know that Pn plus 1, we know that Pn plus 1 equal to Pn plus n plus 1. For Pn, we know that Pn equal to n 3n plus 1 over 2. So we just term into and we substitute with Pn. So n 3n plus 1 over 2 plus 4n plus 1. We look for the question with this 3i minus 1, and we substitute I with n plus 1, and we got 3n plus 1 minus 1. So this settle for this question, and we just simplify the question lah. So 3n square plus n over 2 plus 3n plus 3 minus 1 equal to 3n square plus n over 2 plus 3n plus 2. This time multiple this with 2, and we got 3n square plus n plus 6n plus 4 over 2, and to simplify this term, 3n square plus 7n plus 4 over 2. Since we got left hand side equal to right hand side, Pn plus 1 is true. Therefore, for every integer and element of positive integer and I equal to 1, 3i minus 1 equal to and 3n plus 1 over 2.